So, good day students, and welcome to the last nugget in the lesson dealing with the conversion of biomass to biofuel. What we've done so far in this lesson is that we first spoke about the heating value as a quality measure of fuels. And then we've talked about conversion of biomass into a biofuel by aid of physical, chemical, biochemical and thermochemical processes. The focus has mainly been on the processes as such, and the aim has been to teach you the basics of the processes. But now it's time to have a look at some aspects of the primary fuels produced, and we will introduce the concept of fuel upgrading. So we are now back at the starting point of this lesson basically, and that is, what is fuel quality? Maybe you recognize this slide. It's a copy of the second slide from the nugget on fuel quality and heating values. What I said then was that the fuel quality is a measure of how well the fuel is adapted to the end user process demands. And that still holds true. In many cases, may the end user have fairly strict demands on the fuel as such. For example, may the end-user process be sensitive to small fly ash particles, like in a gas turbine. In that case, is the ash content and the tendency for small ash particles to form a crucial quality aspect. In other cases, may any corrosive components in the fuel be disastrous to the end-user process. Or maybe is the production stability the most crucial factor? And in that case, may the fuel homogeneity be the determining factor for which fuel can be used. So you will realize that each end user will have their own demands on the fuel, and so it is impossible to cover all fuel quality aspects. But what I want to do now is to point out some things for you, things that might not be obvious from the beginning. So what I want you to understand is that fuel upgrading is by no means as simple as some people sometimes will want to tell you. And then I want you to understand a little bit about how to think about these things in real life. The first thing I want to point out is that many of the processes I've mentioned before are really two-step processes. So the conversion process itself will give you a primary fuel. And then there will be a subsequent upgrading, purification or cleaning process before you actually have the final product. Like in fermentation. The primary product will basically be water with some 15 to 20% alcohol in it. Then this primary product is concentrated by separating the ethanol from the water by some adequate process. On this slide, I've put up some things that will be brought up for discussion. And I will try to do it in a reasonably systematic way so that you grasp the underlying ideas. Remember, there are no finite answers to what a high-quality fuel is, but there will be a finite answer to the question if a fuel works well in a specific application or process. So the important thing is for the people in the planning group to ask the correct questions and to identify the correct aspects. And that is what I will try to introduce you to. The physical processes to make biomass combustible or to influence the properties of the biofuel include mainly drying, milling and compaction. In these cases, is there no need for a secondary process. So these are one-step processes from which the primary product is also the final product. None of these processes will change the composition of the dry substance. So the heating value of the dry substance, as for the dry and ash-free substance, remain constant. But if the process involves drying, then will the heating of the moist substance increase. Drying, that is the evaporation of water, is very energy demanding. So for drying to be feasible from an expense point of view, will the drying energy have to be cheap, like sun and wind. For the same reason, the fact that the dry substance composition remains intact, will the ash content and the ash properties also stay the same in the final product as they were in the untreated biomass. So any formation of submicron particles or corrosive gases will remain the same once the fuel is actually used in the end-user process. Now let me just add some comments on other aspects that may or may not be relevant in the specific case. I already mentioned in a previous nugget that the energy density is a crucial measure for the transport economy. So I will not spend any time on that here and now. But I will want to expand on one aspect just to make you understand a bit of the complexity. A common way to install wood chips fired boilers is illustrated schematically at the bottom of this slide. Incoming trucks unload the chips into an underground receiving hopper. The chips are then transported by a centerless screw to the top of a hopper, serving as an intermediate storage. And then the chips are finally fed into the boiler via a horizontal screw or maybe a pusher. The thing with this layout is that the truck unloading becomes very simple since it is on ground level. And the feed to the day hopper is inclined upwards, so fire cannot spread to the underground hopper. By the boiler is only a small amount of chips. The connection between the boiler and the feed hopper is horizontal or may even be inclined upwards, so as to make it simple to install devices to prevent backfire. The screws used in this type of installation are usually centerless. Centerless screws are lighter than screws with a shaft, so frictional wear is reduced. They are also less rigid, so any slight bends are automatically compensated for. The elasticity also makes the system less sensitive to variations in fuel particle size or hardness. One drawback of this installation is that the shorter you make the distance from the boiler to the receiving underground hopper, the steeper will the first conveyor become. And a reasonably compact installation is usually strived for. Since the screw is centerless, will too steep an angle end up with the fuel falling backwards through the screw center? This is not a very big problem with chips, because the friction between one chip and the other will be significant, and a centerless screw can well be installed at a 45-degree angle to horizontal and still work fine for the transport of chips. But if you have a screw at 45 degrees and you try to change fuel to pellets because you want to save transport money, then it will not work. Simply because the pellets have a smooth surface and they will slip back through the centerless screw. So pellets, a nice fuel with uniform size, uniform density, constant moisture, minimal bridging problems, and on the whole a wonderful fuel, would not be a better fuel in that installation. Not because pellets is a bad fuel, but simply because it would not work. So this is the type of questions that I will want you to understand that you have to ask when you're working with the planning of an energy system. As for the chemical conversions performed at more or less ambient conditions, you will remember that the starting point was basically vegetable oils. If the oils are clean from the beginning, will these processes again be one-step processes? So the primary product may be sold as a fuel, unless the end user has some strict demands. If HVO is to be used in airplanes, for example. Because if that is the case, will you have to separate out everything that might solidify at temperatures like -40 or 50 degrees? Many natural fats, and the liquid ones are called oils, tend to have lower heating values in the range 35 to 40 megajoules per kilo. This value will not be significantly different in the primary product. nor will the density change significantly, so the energy density will be similar when comparing the feedstock to the product. If the feedstock is residual oils that may contain different types of contaminants, will the oil first have to be cleaned and filtered. So such a preparation will reduce the amount of non-combustibles and ash-forming elements. But in the basic process schemes, is there no process step to remove the ash components, so that is only depending on the pre-treatment. Now, pure vegetable oils are generally low in ash minerals, in chlorine, sulfur and other elements that may cause problems in combustion. And the processes do not add significant amounts, though potassium and or sodium hydroxide may well play a role as catalysts. So the processed fuels are, from an overall fuel point of view, like ash content and heating value, very similar to the feedstock. And, as a matter of fact, can unprocessed vegetable oils be used just as they are in low to medium RPM diesel engines or in some types of burners. But the problems associated with using the unprocessed oils are first that they will have a variable quality. They will be less homogeneous than the processed fuel. And the second thing is that the unprocessed oils will tend to oxidize if stored for any prolonged time. So if you want to use vegetable oil in a stationary application, in a location where the oil is produced and where you do not have to store it for more than a few days at the most, then you may not have to process it at all. Just see to that it is not contaminated, because if it is, then the engine may break. The engine must also be robust, and it may not run at a high RPM. Such engines will become heavy, and that is why this is first an option for stationary, small-scale heat and power generation applications. But then, if you want to make storable fuels for high RPM mobile engine applications, or if you want to allow the fuel to be stored, then you have to apply processing. As for the biochemical conversion processes, things are completely different. These processes are usually performed using a feedstock that is actually a water slurry. So it is obvious that a conversion is necessary to get a combustible substance out of that. Both these processes are basically two-step. First there is a conversion, and then an upgrading. Raw biogas may be used as a fuel in a local or on-site application, but if you want to sell it, store it, or inject it into a pipeline system or anything like that, then it has to be upgraded first. In the case of alcohol fermentation, will the primary output be an aqueous solution of ethanol in water? But what will also be in that water is anything that was present in the feedstock and that is soluble in water. So if there was sea salt, then will sodium and chlorine still be present in the fermenter output. Or if there was water-soluble mercury salts in the feedstock, then will the mercury remain in the fermenter output. And any other water solubles will also remain in the output. So basically will all elements that entered the fermenter in the liquid input also leave the fermenter in the liquid output. And that represents the ash in this case. The next step in the production process is the separation of ethanol from the aqueous solution, in which the ash components and any corrosive components and contaminants are. And this separation is also the step in which the water content, and hence the heating value, of the final fuel is determined. So the final quality of the ethanol fuel is all set in the distillation process, or to put it more general, in the separation and enrichment process. In anaerobic digestion will this become totally different, because in this case is there a phase separation already in the reactor. in the digester. The feedstock is a slurry that may well contain quite high amounts of what we may call ash minerals, chlorine, sulfur and other things. But what comes out of the reactor is a gas. The atmosphere inside the reactor tank is basically oxygen-free, so the compounds leaving the reactor are non-oxidized. Some of the incoming sulfur will form gaseous hydrogen sulfide. A small amount of the incoming chlorine may form hydrochloric acid gas. There will be ammonia and maybe traces of hydrocyanide. But there will be no calcium compounds, no potassium compounds, no sodium compounds. So the gas will still contain at least parts of some of the original contaminants like chlorine and sulfur and nitrogen, but there will basically be no metal ash components. The primary biogas, the gas from the reactor, is combustible. It is not a wonderful fuel, but it can be used as it is, even in a diesel engine. It is corrosive, so the engine will certainly need a regular maintenance, but at least it is ash-free. So if you want to set up a small local heat and power generating facility, say for a single farm or so, then that will work. But if you want the gas to be a commercial product, you will first have to wash away all the unwanted ballast gas and the corrosive gases. For a commercial product, whether you want to inject it into the fossil gas pipeline system or you want to market it as a car fuel, you will first have to reach a methane content about or exceeding 95%, and then to meet quality criteria you will most often have to add a little propane to it. That gas, commercial quality biomethane or commercial quality biogas, is free of ash and free of contaminants. As for fuels from pyrolysis processes, there are good reasons to distinguish between the products from a rough temperature perspective. You will know that this is not as simple as to say that charcoal is a low temperature process, pyrolysis oil is produced at intermediate temperatures, and pyrolysis gas is a high temperature product. But right now, I want to use that simplification anyway. As for these processes, is the torrefied material immediately ready for sale? There is nothing more to do about the torrefied material. The primary pyrolysis oil is a water-rich mixture of different compounds and contaminants and must be purified prior to use or prior to commercial trade. The primary pyrolysis gas may be used internally on site, but if you would like an external customer to pay for it, it will have to be upgraded. Torrefaction is performed at a low temperature, say 300 to 350 degrees. Already under these conditions may well about 50% of the chlorine and the sulfur be released in gaseous form. So what that means is that the solid product will contain less of the two contaminants sulfur and chlorine than the raw material did. The alkali metals, mainly sodium and potassium, together with other ash minerals, will remain in the solid product. Since there will be a weight loss because of the devolatilization, while the main part of the ash will remain in the solid, will the ash content expressed as a mass fraction increase. Since the idea with torrefaction is to produce a solid fuel, will the process be set so as to minimize energy losses. But there will be a significant loss of mass through devolatilization, and much of the gas lost will be non-combustible or have a low heating value. That, in combination with the drying, will increase the heating value in the solid. Torrefaction is sometimes mentioned as a suitable pre-processing of wood pellets for co-firing with coal. Or not only wood pellets, also straw pellets or other organic pellets. And torrefied wood pellets are sometimes called green coal. In co-firing, you would typically mix the pellets with the coal prior to the coal mills and then mill both at the same time. But you might as well mix common, untreated wood pellets with the coal. The coal mill will mill them too, just as it will mill torrefied wood pellets. Torrefied pellets and fresh pellets will certainly give rise to small differences in the combustion chamber, but the question that must be asked is this: are the differences in combustion behavior big enough to motivate the expense associated with torrefaction? In case the desired product is pyrolysis oil, will the temperature typically be a bit higher, like 500 degrees C. At this temperature, like in torrefaction, will the main part of the alkali metals still stay in the solid phase, and so will the main part of the ash minerals. So the ash content in the liquid product will be low, typically less than 1%. Sulfur and chlorine will escape from the solid to a higher extent than in torrefaction. To a great extent, may these two elements be present as methyl chloride and hydrogen sulfide. Both these compounds will have high vapor pressures. So, if that is the case, will they not enter the liquid phase unless the condensation temperature is very low? Part of the hydrogen in the feedstock will escape in the form of water vapor. So the primary pyrolysis oil will typically have a very high water content. More than 30% by weight has been reported. To produce a pyrolysis gas will, as you know, the heating rate and the process temperature both be raised, maybe up to 1000 degrees. At that temperature will just about all sulfur and chlorine be present in the gas phase. And quite a lot of the alkali metals will also be present in the gas phase. Potassium chloride, potassium hydroxide, sodium hydroxide, and several other compounds, including combinations of sulfur and chlorine, have high vapor pressures at this temperature. Low volatile metals like iron or nickel will stay in the solid phase. But a large fraction of those ash components that are the origin of submicron particles will be present in the fuel gas. Generally speaking, will the pyrolysis gas not consist only of volatile hydrocarbons? The gas will be diluted by carbon dioxide and water vapor, which are both formed during the devolatilization. So the heating value of the gas will be about the same as the heating value of the dry substance. Hydrothermal liquefaction produces a biocrude which is usually very acidic and has a high water content. Most of the calcium from the feedstock will be found in the crude oil, and so will potassium. The oxygen content in the primary oil is also too high for a chemical stability, so the biocrude must be processed to become a commercial fuel. The yield will depend strongly on the process conditions, but total energy efficiencies exceeding 80% are reported. Thermal gasification is, as you know, a high temperature process. The high temperature, that goes without saying, will vaporize anything that can be vaporized at the process temperature. This includes several chlorides, sulfides, and alkali metal compounds. So the product gas from a gasifier will generally contain most of the corrosive components from the feedstock. Also will the main part of the alkali metals, mainly sodium and potassium, be present in the product gas. The alkali metals plus sulfur and chlorine are the components that build up a major part of the submicron fly ash particles. So the fuel gas produced in thermal gasification will actually contain a great part of the most problematic ash elements from the feedstock. The fuel gas will also contain most of the water entering the reactor. Part of the incoming water will contribute to the char gasification, but parts will inevitably only act like an inert ballast gas. So if you want to use the primary producer gas as a fuel in anything that is sensitive to corrosion or to erosion, like a gas turbine or a high-tech internal combustion engine, then you will first have to clean the primary gas from ash elements and from corrosive compounds. The total mass flow to the gasifier is the solid material plus the gasification agents. These agents can be air or oxygen-enriched air, or pure oxygen, or steam, or oxygen plus steam. Regardless, is the total outgoing mass flow always equal to the mass flow of feedstock plus the mass flow of gasification agents. But the energy input is only that which is represented by the heating value in the solid fuel. So the heating value of the product gas is always significantly lower than the feedstock heating value.